Okay, so here is a n-link manipulator, and let's say that there is a gripper. This is the nth link, and we want the gripper to perhaps pick something. So we want to place this gripper not only in the right position, but we also need to place it in the right orientation so it can grip something. If it's not in the right orientation, it cannot grip the object. So the end effector position, we want to specify a reference for the X, Y, Z. But we also need to specify the orientation, which would be P. In our convention, we have P, theta, and psi. So this is the desired or reference end effector position. End effector position / orientation. Okay. Okay, now one thing to know, realize is that since the end effector has 6, well, the position and orientation is given by 6 numbers, which I put there, we want to be able to do that with at least 6 joints, right? Because 6 numbers, 6 constraints posed by the 6 numbers, we need at least 6 joints. If you have more joints, then it's good, but if you have less than 6, then you may not be able to do what you want to do because you pretty much are going to be less of 1 degree of freedom. So we need at least 6 degrees of freedom. Okay, 6 degrees means 6 joints. And when I say 6 joint, I really mean controlled joints. 6 controlled joints. Okay. And that's why when you look at manipulators in the industry, you'll see that most of them are actually 6 degree of freedom manipulators. Sometimes they would have a 7th degree of freedom to give you more control over things because you have an extra degree of freedom. But adding a motor, a 7th motor and 7th joint is expensive. And so they try to restrict yourself to 6. Now, there's one more degree of freedom. Usually with the gripper, you can have a gripper which goes grip or let go. So that is not part of the 6 degrees of freedom. That would be an additional degree of freedom. So what we have seen so far is that given the DH parameters of this manipulator, we can compute the end effector position. So given DH, we can compute end effector position and orientation. Okay, so that calculation is basically you compute the homogeneous matrix by combining all the H's, so on till H n minus 1, and then it will always be of this form: Rn0, Tn0, 0, 1. Okay, and this you want it to be at X ref, Y ref, Z ref. And then this is less clear. This is a 3 cross 3 matrix. Now, how can you get a 3 cross 3 matrix to be equal to phi ref, theta ref, psi ref? Well, it turns out that for a given phi ref, theta ref, psi ref, in let's say in the 3-to-1 Euler configuration, will give you a rotation matrix. And from that rotation matrix, you can actually extract out phi, theta, and psi. So the way it is done is follows. Okay, this was actually one of your homework question, I think. You were given in the 3-to-1 configuration, or 3-to-1 Euler angles, we had computed the rotation matrix. So rotation by the z-axis, then y-axis, then x-axis, and you get this whole big 3x3 matrix, right? So this is going to be your Rn0 because you're trying to place the end effector at that position. So just from some of these, just by looking, well, let me just write it down this way. We can write this as R11, R12, R13, R21, R22, R23, R31, R32, R33. And so if you want to compute theta, psi, and phi, what we'll do is we'll look at the simplest possible elements of this. So we can see that row 3, column 1 is sine theta, and that's probably the easiest way of computing theta. So minus sine theta is, so theta will be theta ref equals R31. And so in order to figure out theta ref, it's going to be simply sine inverse of minus R31. Okay. Once we get sine theta, we can use either this or this, it's up to you, to compute phi. So this is, let's call this 1. This gives us theta ref. So from, let's say, row 3, column 2, we have cosine theta ref sine phi ref equals our third row, second column. Okay, but we know what cos theta ref is. It's computed here. So all we do is we compute phi ref as sine inverse of R32 divided by cosine theta ref, where we'll substitute this theta from equation 1 over here. And once we do that, we have everything else in the bracket is known. And so we can compute phi ref. That's number 2. And then the third step is to compute psi, which can be computed either from this or this. It's up to you. So let's just choose, I just choose R21, but you could choose R112. So we would have cosine theta ref sine psi ref equals R second row first column. And so from that, we can solve for psi ref as sine inverse of R21 divided by cos theta ref. And it's the same thing, which will go here. This is 3. And so from 1 to 3, we can compute 3 gives theta, sorry, phi ref, theta ref, and psi ref. Okay, so once we have those, we can then use what we've done before, which is fsolve. Fsolve will basically solve for 6 equations, 6 unknowns. So 6 equations are, these are the 3 equations, 1, 2, 3, which I've written, but then the other 3 will come from here. This will give me the remaining 3. Let's call it 4, 5, 6. Okay, so let's solve a problem based on this. Okay, the problem is, okay, here's the manipulator. Okay, this is how, well, this is just not even a CAD rendering. This is just a figure which was in some book. What I did was I took that figure and then broke it down into a DH table and a DH table, which is here. And then this is the figure, which corresponds to this. So the way I went about doing this was the same way. I know the link joint one axis, it's like this. link to axis and so on. I just went about fixing the z-axis, then fixing the x-axis and so on, and then got the table. This manipulator is actually known as a Stanford Manipulator because it originated from Stanford in, I think, the 70s or maybe even before that. Okay, and then the question is, first, compute position, orientation of the end effector. We will do a forward. Well, we'll do the when animation for given joint angles, and you can put any values you want for the 6 joint angles, the 6 links, there are 6 lines, rows in the DH table. So here, and then finally, inverse kinematics, which will be given the position, orientation of end effector, compute the necessary joint angles. Okay, so the hardest step, which is the DH table, has already been given to you, and all you need to now do for step 1 is compute hn0, which will be h10, h21, so on till h. Well, here n is 6, right? So h32, h43, h54, h65, and that's kind of trivial because you're given the DH table. So H comes from the DH table. Each row of the DH table gives you a particular H, and then you just have to put it together. Okay, the animation is something I did last class where you just have to do the position of the end effector, the joints of the links by figuring out the axis, the origin of the axis. Okay, and that comes from each of those H's that I showed last time. And then the inverse kinematics is very similar to what we did for a 2-dimensional manipulator where we used fsolve. We'll have 6 equations corresponding to 3 over here, 1 to 3, and then 3 from right here. So there's no point in trying to do it by hand because the system is nonlinear. So we just use Python. So I wrote code which will do this job for me. Okay, so the DH table actually doesn't have the lengths inside, I think. They're just given as L1, L2, and so on. Okay, they are given as D's and pi and so on. So I need to put some value. So what I did was I just gave some values to the various parameters. Okay, and you can expect that you'll get values given to you in some form. So for the homework, you have a UR5, which has particular set of values. And so you use those. So this comes from the specification of the manipulator. The DH function just puts the 4 H's together in this form. and then returns H. My inverse kinematics, well, the heart of the code is not this, but the part where I do fsolve. Okay. The heart of the code is doing fsolve. Fsolve looks at the function inverse kinematics. It needs initial guess. It needs the desired where I want the end effector to be. I've specified some tolerances, termination tolerances, function evaluations, and tolerance on X. It is if the X doesn't change by 1 e -6, it is this one, then it will terminate. Now, X desired is what I said is the end effector position. So I just randomly specified some values. So the position, for example, 0, 0, 0, and then this is the desired. And my inverse kinematics would need those 6 equations, which I can get from in a numerical way. So all I do is, these are my control parameters. So the Stanford Manipulator has 1, 2, 3, 4, 5 revolute joints and 1 prismatic joint. That's where the D versus theta. And then I assemble the H matrix by calling the DH function. So I get H06. So for end of link, I said it's the 4th column in the first 3 rows of the 4th column. So 0 to 3, so 0, 1, 2, and 4th column. So that gives me the end of link 6. So it will have 3 things in it, X, Y, Z position. I take the rotation matrix corresponding to the first 3 rows and first 3 columns of H. I use the same formula I wrote down in the notes, compute theta, phi, and psi. And I need to return what is known as the errors. So end of link 6, the X position with X desired, end of link, the Y position of the end effector with Y desired, same for Z, and then for the angles. So I run this. It will do an animation. Rotate this. Okay, so you can see 1, 2, 3, 4, 5 links. I think 1 link is of 0 length. That's why it is showing only 5 links. Okay, but that's where I want the manipulator to be. I've not really shown a gripper, but trust me, if I'd shown a gripper, it should be the right orientation I desired, which would be 0, 0, 0. So it's inclined at angle of 0 to all the 3 axes. So you can change the desired position the way you want, and then it will do that thing. If it's beyond the reachable space, then it will not start that. So this is a simple example which we did for the 2 link. Let's say that this is O, this is P, this is Q. All you do is you set up a line between O to P, and then line from P to Q. Now, there is a syntax which I'm ignoring here, but you basically take the x coordinate, we just put it this way, x coordinate of O, x coordinate of P, y coordinate of O, y coordinate of P, that will be 2. And then same thing over here, P1, Q1, P2, Q2. So this is X coordinate. This is Y coordinate. Okay, so once you have this, you can just use line to draw a line between them. In order to do 3 dimensions, this is all in 2D. In 3 dimensions, this is just extending it in the following way. You use a line, but then you give it 3 coordinates, P1, O2, P2, O3, P3, and so on. So this is X, Y, Z, and then you just keep joining the points, and then you have the position, well, you have the endpoint, so you have basically the links, and once you have the links, you have the manipulator. Okay, now how do you get these links? How do you get the endpoints? You have to use H's. So H01 will give you so you compute H01, H10, H20. This is known. This is H21, H10, H21. H30 is H10, H321, H32. So this gives you RO01. This also have an RO01. These R's would be different. It'll be 10, 10, 21, 21, 32, sorry, 20. Everything is going to be in the base frame. So 3, 0, 3, 0. So this is what you're after. This thing gives you the position of end of link 1. This is end of link 2. End of link 3. Okay, once you have that, this is what will go here. Okay, so I'll show you an example where I do this, but essentially you're looking at the H, which comes from the DH table, and then you're just looking at the fourth, since a 4x4 matrix, it's basically the fourth column, the first, second, fourth column, first, second, third row. So O10 would be X, Y, Z, and so on. This X is the one which will go here, the Y will go here, the Z will go there. Okay, so this is very rough, but you have to really look at the code to understand this. It's much easier than trying to write it down. Okay, so I'll show you code which will animate a manipulator. So first I did a two-link example. Okay, so that's just some angles. This is the first example we did in the class. Okay. Okay, so there's an H matrix, and the H matrix is composed of 4 multiplications. Now, you could either do this multiplications and get the formula like I wrote it here in the handout, or you can actually not do the multiplication ahead of time. You can just assemble the H by doing this 4 transformations. There's composed of alpha, A, D, and theta, and that's what I chose to do. I just kept it as individual H's, which I then multiplied together to get the H. To get H01, I just take the DH and pass the A, alpha, D, and theta. Same for H12. And then, as I said, end of link 1 is nothing but the 4th column. Sorry, this is the 4th column, which is 3. And then the first, second, third row, which will give me the X, Y, Z. Similarly, end of link 2 will come from H02, which is a multiplication of H01 and H12. And again, I compute the 4th column, first, second, third row is the X, Y, and Z. To make the animation, essentially my manipulator starts off at 0. So I just put 0, 0. And this is 2D, so I just did not bother with the third dimension because it's a 2D plot. So X, Y, for this end of link 1. So that's the first line, the blue line, which I showed in the animation. And then the red line was end of link 1, end of link 2, and so on. That came from H02. Let's see on this again. Control Shift P. So 0, end of link 1, X and Y, end of link 2, X and Y. So that's something we've done before. Here is a more complex example, 3-link manipulator. Okay, so a 3D plot, and let me just pause it. Okay, so 3 links, red, blue, and green. And let me see what I did for the DH. So for the DH, theta 1, theta 2, theta 3. This is I think this is the second example we did. That is the first example I did today in the class, where D1, the first link, the theta 1 was, so it's a RPP manipulator, where first one revolute I can specify, and then this D and D2 and D3 can be specified. Okay, so the DH function is the same, it's copy paste, nothing different there. That's a DH function. It basically returns the homogeneous matrix H composed of those 4 multiplications, so return H. Then H01, H12, H23 is straightforward once I have the A from the DH table, which I wrote down. Yeah, it is the second example, because remember it was either minus 90 or 270. In fact, if I change this to 270, I think I'll get the same. So if you remember this, just remember this configuration, and I'll redo this with 270 degrees, and you see that you get the same figure. 270 is 3 pi divided by 2. Get the same thing. So minus 90 is the same as 270, give the same answer. Okay, so end of link 1 is H01, the first, second, third row of the 4th column. End of link 2, I need to compute H02, okay, which I've computed here, H01 times H12. Again, the first 3 rows of the 4th column. End of link 3, H03. And then to make this plot, this also gives you the position oriented, the end effector if you need it. And then in order to create the plot, I just go plot X, Y, Z in some color. Then the X coordinates of link 1, link 2, Y coordinate of link 1, link 2, and then the Z coordinates of link 1, link 2 with a blue and then light blue. And here in this case, it's a 3-dimensional figure, so you can change the azimuth and elevation. This is just to give a different feel, so different viewpoint. So if you change this to, for example, 90, it gives a different view. And then the way to figure this out is you can actually rotate it the way you want. And you can see that it's popular. On the bottom right, it gives you the azimuth and elevation. So let's say you like this configuration. It says azimuth is 64, elevation is 29. So go here, 64, and I think it's 29. You got the same one as you. Okay.